If you were a marine organism, where would you live in the ocean? And what factors would influence your decision? Would you live somewhere warm, with plenty of sunshine? Or is an underwater cave commune with all of your closest friends more your style? Perhaps an old shipwreck where you could spend your days exploring and have a place to hide from predators.
How about here? While this may seem cold and murky to us, it's perfect for phytoplankton and many other organisms on the trophic pyramid that rely on those phytoplankton for energy. So, let's find some place warm and dry and talk about all of the environmental factors that affect life in the ocean.
Well, this is certainly better, right? Well, humans have definitely come up with interesting ways to deal with cold temperatures. We're certainly not adapted to it necessarily, right? We evolved in sub-Saharan Africa where temperatures stay pretty warm. So we're happiest when we're warm. And that's not necessarily the case with all organisms. So the first thing we want to talk about in the ocean with regard to these factors that affect life is temperature. And this is important because for all organisms, temperature has a big effect on metabolism. So first thing is we remember sort of the general way temperature looks in the ocean. Now this is going to vary between, again, the tropics and the polar regions. But we know that in the surface ocean, it tends to be a bit warmer because of the sun's energy. And as you go deeper, it gets colder. Great. Well, what we also want to know is that as temperature goes up, metabolism goes up. And when I say metabolism, this is back to our discussion in primary production about things like photosynthesis and chemosynthesis and cellular respiration for us, right? So you can sort of think of it like on a cold day, yes, you know, there's some outdoor sports, but it's nice to stay bundled up by the fire rather than, you know, running around outside in shorts and a t-shirt. And as the temperature goes up, we get a little more energetic. And the same sort of thing happens metabolically in our cells. As temperature goes up, that metabolism goes up. And it keeps going up at least to a certain point, right? After that, it kind of drops off rapidly, and then you're sort of in the area of saute or boil, or it doesn't matter. We're not going there. We're not cooking anything. We're just saying that, you know, these metabolic processes go up a little bit as temperature moves up, and we get into our comfort zone. And again, it's different for different organisms. And every organism in the ocean and in the world has different ways to deal with it. And there's two big categories here. You may have heard of these before, something called endothermic and ectothermic. Now the terms you may have heard are warm-blooded and cold-blooded, but I really don't want you guys to use those again because they really don't make sense. They don't tell you what's actually going on. And I say that because warm-blooded, the actual term is endothermic. It means we can create our own temperature, things like us. So we always have an internal temperature of around 98.6 degrees Fahrenheit because our body regulates this and it tries to keep us warm. We shiver to keep that temperature up and we sweat to keep it down, right? So we self-regulate our temperature. And in the ocean, we have endothermic animals as well. So many of the all of the mammals, right? Birds, some of the bigger fish, they are endothermic. They can regulate their own temperature. And then the other one, again, term to never use again, cold-blooded, is actually ectothermic. And that just means they rely on the outside temperature for their own. So as the temperature goes up, their body temperature goes up. And as the temperature goes down, their body temperature goes down. And these are things like most fishes in the ocean, marine reptiles, right? I guess they have to deal with whatever's around them. And so you might see something like an iguana sunning itself on a rock. Well, what they're actually doing is they have to use the sun to heat their body up after swimming around in that cold water. So their temperature goes up and down. And it might look a little something like this. So if you had a figure, you had a graph, and on one side you had the internal body temperature, and on the other you had the outside temperature. Well, this diagonal line here, right, would be those ectothermic animals. right? They're beholden to whatever temperatures around them, and they have to find ways to heat themselves. So as the temperature goes up, their body temperature goes up. And then endothermic would just be a straight line across the top. For the most part, us mammals and other endothermic animals regulate their own body temperature, and it stays pretty much the same. Now, granted, we have to, if it gets cold, we have to go and dress warmer to keep that temperature, but we have to maintain that 98.6 degrees. Anyhow, temperature is just one thing, right? It's one thing that affects these food webs. It's one of our environmental factors. Other environmental factors, now, there's a lot of them, right? And you can get really creative, and I really appreciate the answers that you guys gave on that class participation. We're going to stick specifically to only a few that really affect this food web balance. So in general, an environmental factor is any aspect of the environment that affects an organism's ability to thrive, right? It affects its longevity. And these are things like temperature, and we're also going to talk about light. We're going to talk about pressure. So a couple things we've already kind of touched on. Salinity, we've already talked about that a little bit. And then we're going to move into things like dissolved nutrients and dissolved gases and talk a little bit about the acid-base balance in the ocean. So now that we've discussed temperature, let's move into light. Now, you know, we've already seen that you can be somewhere where there's plenty of light in the water, or somewhere out here in Narragansett Bay that it's a bit murky and it's not so clear. However, both of these places in the ocean are still that surface zone. They still contain light. And believe it or not, the vast majority of the ocean is completely dark. So if we take ourselves out of our nice, warm, cozy chair and put ourselves back underwater, all right, we can see that there's light coming in. And again, like I said, this is not most of the ocean. So let's take a look at sort of a profile of the ocean here, right? So here's your continental shelf, right? We're still on continental margins off the side. And this actually goes down to about 9,000 meters. Now remember, average ocean depth's about here. And what this is showing you is that there's a zone right up here at the top called the photic zone, where light actually shines. And the rest of it is aphotic. And this is what we care about. We'll talk about this dark region a bit later. But what we want to do is we want to zoom in and look at this photic zone. All right? And even this photic zone right here is divided up. So if we take this section and we look at it graphically, figuratively, and this whole thing is a photic zone from up here at the top down to about here. And like I said, you know, right now it's saying about 600 meters or so. This is very, I shouldn't say arbitrary, but it's a generalization. This can vary quite a bit. But just note that, you know, 600 meters is far, far shallower than the average depth of the ocean. So the whole thing is the photic zone, right, where we actually get light. Below that, there's absolutely no sunlight. And then there are two main divisions within the photic zone. So up here at the top, the really, really skinny part is what we call the euphotic zone, all right? That means good photic, right? That's the good light. This is where there's plenty of vision, there's enough light for photosynthesis, right? And that's an important part for these environmental factors that affect metabolism, specifically photosynthesis, right? There's enough light for that. And then you get into something called the dysphotic zone. And there's still light, but it's really murky. There's definitely not enough light for photosynthesis, and things have to have really big eyes to live there to see anything. There are a few creatures here that create their own light. You know, that's kind of saved for even the deeper depths. But this is how we break it up. And, you know, while I show you these, and then, and by the way, the aphotic zone is below that. I think I already discussed that a little bit. This is also not really a good representation. So I like this figure because, again, it's going to show you, it's a nice thing. It shows you sunlight up here at the top. So again, the euphotic zone. Then you have less light in the dysphotic zone. And then this midnight, the aphotic zone. But sort of like the continental margin figure I showed you, we've expanded this to be able to even see this part. So if I squish this down to what it actually looks like, all right, I'm going to expand the aphotic zone, and I'm going to take that photic zone is only up here, and the really tippy top, the little tiny sliver of light, the euphotic zone is where all of the photosynthesis happens, right? This tiny sliver of light is where that half of the Earth's primary production occurs in the ocean. Really, really small. So that's, I don't know, that's pretty amazing. Not only that, but not all light is created equal. So if we go back here underwater, all right, and the sun's shining in the top and the light's coming in, well, the light starts to break up. This white light breaks up into different colors like a rainbow. And this is because of something called the electromagnetic spectrum. Now, we don't need to go in detail here, but just know that visible light is a really small part of this electromagnetic spectrum that encompasses things like radio waves and microwaves and your Wi-Fi, and that visible light's very small, and that's broken up. Again, just like the colors in a rainbow, you know, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, look at that. And it's based on their wavelength and their frequency. And because of this, and because of the way water works, is not all wavelengths penetrate the same distance. So let's start with red. And if I take this white light and shine it in, well, this red light is only going to go so far, and it's going to stop. So below that, you still have light, but you can't see red. So if you guys have ever been somewhere where, you know, again, enough light penetrates, and you take something red underwater, it's going to start to look like brown or green. Like those colors just don't make it down there. You actually have to bring your own light to see them. Well, carrying on, you know, next we have orange, and if we take that, it goes about that far. And so on and so forth. You know, the next one, green, it goes a bit further, actually quite a bit further. And then finally, the last light to penetrate, this blue light, actually makes it down the furthest. So in that euphotic zone, or even, actually I should say, even in that dysphotic zone, it's the blue light that penetrates furthest. So remember that, the blue light penetrates furthest, and it's based on wavelength. So that's light. So now we've talked about temperature, we've talked about light. Both of these things we can see directly related to photosynthesis and cellular respiration. The next one we're going to talk about is pressure, and this one's actually pretty quick. So pressure is pretty important in the ocean. All right, we already know hydrostatic pressure equation. We know the deeper you go, basically the pressure goes up, and it's fairly linear. So organisms that live in the bottom deal with some incredible pressures. Well, as it turns out, it doesn't matter that much, okay? Most organisms, including us, are filled with water also. And so the pressure on the outside pretty much equals the pressure on the inside, and they don't notice it that much. We have a hard time with it because of our air spaces. But organisms that don't have any air in them, basically, it's not that big a deal. So that's pretty much all we're going to say about that. Now, the flip side of that, the reason I do want to talk about this is sometimes it has the opposite effect. So we've already talked about chemical reactions, and we've talked about the energy transfer, and one other aspect of this is the pressure that surrounds these chemical reactions. They actually affect how they move. So there are certain organisms, microbiology usually, that live in these incredible pressures. They do some amazing chemical reactions to survive, and as it turns out, they would be completely unable to do those at the surface of the ocean. There's just not enough pressure to make those happen, and they can't survive. In fact, a lot of the work I do and with colleagues of mine, it gets really difficult to study these microbes because you can't grow them in the lab. They just keep dying, right? They don't survive that trip to the surface. So anyhow, that's pressure. All right, the next one we're going to talk about is salinity. And I know we've talked about this a lot, right? We've figured it out. I've given you guys charts and made you figure out salinities based on density. But we haven't really talked about what salinity is. So if I take, let's say we're back down in the water. Let's say I just take some pure water, all right? So this is about a liter, right, a bottle of water. And when we're looking at these figures, right, we're looking at this temperature salinity diagram, what we're really looking at, you know, this PSU, and something else I've told you about is this per mil, this per milli. What that means is, let's say, again, this is a liter, so this is about a kilogram. This is about 1,000 grams, all right? So in 1,000 grams of water, you have about that much salt. That's about 35 grams, all right? So that means 35 grams of salt per 1,000 grams of water. That's where we get the 35 per mil. So I'm going to ask you guys this again on your questions about what the average salinity of the ocean is, 35 per mil. And that's how that works out. All right. But again, what does that mean? What does salt actually mean in the ocean? Well, let's break that down, all right? Because it's not just one thing. And this is the way the surface salinity looks in the ocean. Now, this varies quite a bit. Like we said, the average salinity is, you know, right around here, and you can see that there are areas where that changes quite a bit. But again, this is surface salinity, and it's not all that much. But even this little bit is going to affect the way organisms grow. Having salt inside and outside of their bodies can affect the way nutrients transport back and forth. It can affect the way they do some of their metabolic functions, all right? So this becomes important. And it all has to do with the things that make up salinity. So again, you know, just looking in the water, if I break this up, I get something like we sort of saw in the atmosphere. So this whole thing, right, this is my kilogram of water, all right? This is my 1,000 grams. And this small sliver here is that handful of salt, all right? 35 grams per, again, a total of 1,000 grams. That's what that is. So then if you take this salt and break it up, what it actually means is it combines a few things. Now, the most abundant is sodium and chloride, and that's basically table salt, all right? Sodium chloride is your basic salt. Well, I don't know if you guys have ever gargled with salt water before if you're sick, but it doesn't taste like the ocean. I mean, hopefully you haven't drank a lot of ocean water, but ocean water has that sort of a bitter taste. Well, that is because of a lot of this other stuff. In fact, magnesium is one of those things that gives it that taste. So there are some minor constituents. But importantly, salinity is the total amount of dissolved inorganic solids in water. That's what we define as salinity, all right? And this is where it's going to affect this transfer of nutrients and metabolic functions. Okay, well, dissolved inorganic substances, does that help? Does that tell you much? Well, let's figure out what that is. And we're going to look specifically, don't worry too much about these minor constituents. You know, we're going to talk a lot about sodium chloride. So if we pop back in the water here, let's look at something you guys are already familiar with, right? The periodic table. And we already know that this is organized, you know, the different elements based on their atomic mass. And we can find sodium. Sodium's right here. And we can find chlorine. Chlorine's right there. And that's what we want to focus on. We want to focus on these two elements. And you already know that the one thing it shows you, this bottom number here, is their atomic mass, right? That's how much mass these things have. Well, we haven't talked about this other number, this 11 and this 17, and that's the atomic number. So the way atoms are structured, right? If I show you a sodium atom and a chlorine atom, well, right there in the middle, in the nucleus, is most of that mass, okay? And that's formed of neutrons and protons. And that's where you're able to figure out what these numbers mean. So these numbers are the number of protons that are within that nucleus, right? They make up part of that mass. And something else special is those protons are positively charged. So don't worry about the neutrons, they just add mass, they don't worry about charge, but that center nucleus is overall positive. So in the case of sodium, it has a positive 11 charge, and chlorine has a positive 17. So what that can tell you now is about the electrons. And the electrons are the things that orbit, for lack of a better term, the nucleus, all right? And they have a negative charge. So for most atoms on the periodic table, they're just sitting there happy with a neutral charge. So that means the number of electrons have to be equal to the number of protons. And the reason this is important is because these electrons are how these atoms interact with each other, interact with themselves, with other compounds, other molecules, right? This is what makes them do stuff. And I'll show you what I mean. All right, so you look at these two atoms, and we see the nucleus and we see the electrons. Well, there's a lot that goes into the reasons for the number of electrons in those, what I'll call shells, those circles there with electrons on them. But simply put, let's just focus on that outer shell. And in general, an atom is happiest if it has 8 electrons in that outer shell. Doesn't need to do anything, happy, all right? Well, what you can see in sodium's case is it only has 1. And in chlorine's case, it has 7. So a little cooperation here, and both of these can be happy. So what happens is sodium's like, you know what, I don't even need that extra electron. I'm happy, let me just get rid of that, and I'll have 8, and I'll be fine. And chlorine's like, well, I could probably help you out with that because I wouldn't mind having 1 more. So what happens is sodium takes that electron, right, and it donates it to chlorine. And now we've done something to these two. Because that electron is negatively charged, we've removed it from sodium, which means now sodium has an overall positive charge because it still has the same number of protons. But now chlorine has more electrons than it has protons, so it's an overall negative charge. And we've created something called an ion, all right? Ions are these atoms or molecules with a overall positive or negative charge from neutral. And what this means is these two can now stick together, right? Just like a positive and a negative in a magnet, they'll stick together and form sodium chloride. And this is called an ionic bond, right? It's a bond between two ions because of their dissimilar charges. Well, something else interesting happens. If you guys remember from when we talked about water molecules, right? Water molecules are polar. They have a slightly positive end and they have a slightly negative end. And what that means is when we take something like sodium chloride and we put it in water, it dissolves, it separates. Water actually is able to rip these molecules apart because of those charges. And it gets in the middle of it. So that sodium and chloride, they're still there, right? This isn't a chemical reaction. They haven't changed into anything else necessarily. It's sort of a chemical reaction, but they're physically the same thing. They can taste the same thing. It still tastes salty, but you don't have those sodium chloride molecules. They're dissolved. And that's what I mean by dissolved inorganic solids. All right, so enough about that. Something else about the ocean is the salinity doesn't really change that much. It stays pretty constant. So why is that? Why is it always about 35 per mil? Well, that's because of something like this. So don't worry too much about the exact chemicals here. Just know that we get ions from river discharge. We get them from volcanoes and clouds, right, and rain. We get ions from the ocean bottom, right? They actually come up out of the ocean. And then they also go away. So they'll get buried here in the sediment and then down into the earth. All right, so there's a balance, right? The ocean is in this state of equilibrium because the comes-ins equal the goes-outs, right, for lack of a better term. And that's all this means. So the ocean is constantly in this state of equilibrium, again, about 35 per mil. Okay, well, how do we know that? All right, how do we know, if I take my water here, how do I know, oh wow, kind of disappears, doesn't it? How do we know that there's actually salt in here? Well, as it turns out, if you guys have ever done this, if water evaporates, there's salt left behind, but not all of it, all right? Some of it becomes volatile and actually goes up into the atmosphere and disappears. So we can't just evaporate the water and weigh it. And we can't just weigh the difference between salty water and non-salty water either, again, because those ions and those molecules don't necessarily stay put, so we have to do something else. So in water, okay, back in water we go, those ions are broken up. And because they have charges, we can do something interesting, all right? We can actually run an electric current through the water. So your sodium ion is a plus charge, chlorine is a negative charge, right? And you take these electrodes and actually stick them in the water and you'll get a current. You'll get a movement of electrons. So you can measure this current, and this is what we do. It's something called conductivity. And this is how we measure salinity in the ocean. So through some trickery, we end up with a unit like PSU, practical salinity unit, but that has to do with transforming this conductivity, right, into a usable unit that we can use. But importantly, this is how we measure salinity, right? We actually run an electric charge through it and get the conductivity. Okay, so that's salinity. So we've talked about temperature, light, pressure, salinity. What's next? Nutrients. What is this nutrients thing I keep talking about? What do we need nutrients for? Well, if we look at this figure here, we've talked about a couple of these, light in particular. I just want you to focus on this purple line here. And this is the broad idea for nutrients in the ocean. And a nutrient is just something that an organism needs to do its metabolism, either growing or creating energy. Okay, so in photosynthesis, other than just carbon dioxide and water and sunlight, there are other minor constituents that we need. We need them too as humans. You think about your vitamins that you get, vitamin A, B, C, right? These are nutrients. And in the case of the ocean, the primary nutrients that we're talking about are nitrogen and phosphorus, and they come in different forms, nitrates, phosphates usually, and those are actually ions again. But the important part here is that for most of the organisms that, again, live up here in this photic zone, they use them all up. So there aren't a lot of nutrients in that surface zone. It's depleted, so things can't grow when there are no nutrients. So if we look, we've seen this figure before, right? We look back at the Earth, and remember the green parts are high primary productivity, and the blue are low. So we see out in the middle of the ocean, And these gyres, right, all the 5 ocean gyres, is very low productivity. There's no life there. Again, why when you go to the Caribbean, that beautiful tropical ocean is actually quite lifeless other than those coral reefs. But that's because of that nutrient limitation. Well, you'll notice that along the coasts here, and up in the polar regions and actually along the equator as well, are these really bright green spots. There's a lot of productivity, again, especially along the coasts. Well, why the heck are there more nutrients there? Some of them come from land, but not most of them, all right? So let's go back, let's look at this figure again. And where do you see most of the nutrients? Well, they're deep. They're down here. So somehow we have to get all this up to the surface where there's light and photosynthesis can occur. So this is going to take us back into Module 1, and we're going to learn a new current, all right? And we're going to talk about winds again. So if you guys remember this figure here, you guys remember Ekman transport, right? When the surface wind blows, it creates a current 90 degrees, right? Most of that mass transport is 90 degrees from that air current, either to the right in the northern hemisphere or to the left in the southern hemisphere. So let's take it as an example. Here's a nice big spot of primary productivity. And let's say we have this is the Canary current right here, right? Remember, as part of this big ocean gyre, there's a current that comes this way. Well, there's also air, right? These trade winds come down, all right? Well, as they go along the coast, they're going to create Ekman transport. So these coastal winds blow along the coast, and that mass transport is now away from the coast. So the winds blow south, mass transport is this way. Well, you can't exactly just pull all the water off the coast and leave nothing. So something has to replace it. And that's where that bottom water replaces it. And this is something called upwelling, okay? So because of that Ekman transport, because of these wind currents, they actually will move the surface water away from the coast, and you'll get coastal upwelling. Those nutrient-rich waters will come up and replace the movement, the water that moved away. And opposite of that, you get something called downwelling, where the exact opposite happens, right? You get wind blowing the other direction, it pushes water against the coast, and other than big storms, it's not going to push it onto land. It ends up pushing everything down. So overall, this coastal upwelling will bring nutrient-rich waters to the surface, and the downwelling will bring nutrients and dissolved gases to the deep ocean. All right, so there's your nutrients. Well, I also just said something else. I said this downwelling is responsible for bringing dissolved gases down to the deep ocean. Okay, well, here's our next thing, right? What's a dissolved gas? We know what a dissolved inorganic solid is, but how do you dissolve gas? How do you dissolve air? Okay, well, let's think about this. Let's put ourselves in an aquarium, all right? And we've seen this before, right? Why are there bubbles in the aquarium? Is that just because it looks cool? It makes the little sea chest pop up and go back down, right? Buried treasure. Well, there's really a practical reason for this, and it's not because fish breathe those gas bubbles, all right? Fish don't breathe gas bubbles. But they also don't breathe the oxygen that's attached to water. So if you remember our water molecule, right, we have an oxygen attached to 2 hydrogens, but those are pretty steady. That's not really going to go anywhere, at least not yet. They kind of stick there. What they breathe are these oxygen molecules, so this O2, just like we do in the air. But they do it differently. They have to extract it from the water. And again, it's not a gas like we think of. Let me see if I can show you an example and explain this a bit. So if you take a soda, right, and it's closed up, and there's no bubbles in there, right? The soda has no bubbles. And you can see that, but as soon as you open it, bubbles. Closed, no bubbles, open bubbles. Well, why the heck is that? Well, it's, again, because of some physics, right? What's going to happen is, at a liquid surface, there's a balance between the amount of gases in the airspace and the gases in the liquid, all right? And it looks a little something like this. You can see these individual molecules floating around in the headspace and individual molecules floating around in the liquid. So it's not until these molecules start to bunch up in mass that it's going to turn into a bubble. They're just not bubbles. They're individual, in this case, carbon dioxide, but we're talking oxygen molecules stuck in there. But as soon as you open it, as soon as you release that pressure, wow, all that air is going to come out, and then those start to come out. And that's because of that balance. You've now removed the pressure keeping those molecules in the liquid, and they're able to expand and form gas bubbles. All right. So what does this look like in the ocean? Well, as it turns out, unlike the atmosphere, which is pretty stably 21% oxygen and then 78% nitrogen and very little carbon dioxide, it can vary quite a bit, all right? It can vary with location, and it can definitely vary with depth. And what you can see here is, while we have a lot of oxygen in the surface, this is the green line, it goes down rapidly, and we end up with very little oxygen down in the deep ocean. And carbon dioxide does the opposite. It starts out low, but then it actually increases. It goes up. Well, let's see. Why the heck is this? Well, about right here is probably the euphotic zone. So this up here is where all that photosynthesis is occurring, right? We're using up carbon dioxide and producing oxygen. So there's a lot of oxygen up there and very little carbon dioxide. Well, once you get past that lighted zone, all of a sudden, dysphotic, no photosynthesis, right? But respiration is still occurring. So respiration is using up the oxygen. So this dissolved oxygen is getting used for cellular respiration. And, oh, by the way, we're not using up the carbon dioxide like we were. In fact, we're producing some from cellular respiration, so that starts to go up. So that's why we get these trends in the ocean. Something else really interesting about the ocean, right? If I tell you there's actually 60 times more carbon dioxide in the ocean than there is in the atmosphere, that's a lot. Well, I also just told you that there's a balance here. Now, it's not exact, right? Depending on the molecule, there's a difference in the amount of dissolved gases and gases in the atmosphere, but not 60 times as much. So are we violating some sort of physical law in the ocean? Well, not exactly. So if I take and look at the surface of the ocean here, all right, and I say, okay, well, at the top, I have atmospheric carbon dioxide. We know what that is. And I'm totally not going to go back and edit that too. You guys know that's CO2. We know what that is, and it's going to exchange. Just like that surface of the Coke bottle, there's an exchange, and we end up with dissolved carbon dioxide in the ocean. Now, the first thing to say is, I'm not violating any physical laws here. Okay, these are in balance. And again, the numbers are slightly different, but not 60 times as much. In fact, it's actually a bit less in the ocean. So what happens? How do we end up with more carbon dioxide in the ocean? Well, chemistry, chemical reactions. And what's going to happen is that CO2 is going to come in and it's going to combine with the water that's in the ocean. And those are going to combine and they're going to yield this carbonic acid, right? H2CO3. It's a carbonic acid. So now we've already seen, well, this is in balance, but now some of it's pushed over into this other molecule. So we're able to store some in another way that doesn't affect this, this balance up here. Well, it doesn't stop there, all right? That carbonic acid doesn't stick around that much. It actually breaks up also, and it breaks up into bicarbonate and then this hydrogen ion. And we already know an ion, right, with a plus sign is an atom with one less electron. Well, in the case of hydrogen, it only had one to begin with, so this is basically just one little proton floating around, all right? So now we have another area. This bicarbonate is able to store even more carbon from the atmosphere. And it doesn't stop there, okay? This breaks up too. And it's going to break up into carbonate and another proton, another hydrogen ion. And this is something in the ocean, this is a chemical equilibrium again. So this doesn't just go one way, right? The arrows go backwards as well. Each one of these stays in a balance. Okay, like I said, it doesn't hang around that long in this carbonic acid. Actually, quite a lot of what's in the ocean is in this bicarbonate. But the important part is because of this chemistry, because of this chemical equilibrium, the ocean is able to hold on to a lot of that carbon. So this is where that, uncertainty comes from scientists about exactly what's going to happen with the massive input of carbon dioxide into the atmosphere. It gets complicated. It's hard to know exactly what's going to happen. But we do know that there's a limit to how much the ocean can hold. So this is your dissolved gases. And this is your carbon cycle in the ocean. This is how we have more and why the ocean is so important for this carbon cycle, for holding on to these greenhouse gases that we don't want to be up here. So it's doing us a favor. The other thing I want to draw your attention to, again, is back to these little protons, all right? And this brings us into sort of our last environmental factor, and that's something called an acid-base balance. You guys probably have heard of acids and bases, right? So something like an acid, stomach acid, lemons. Bases are things like bleach and ammonia. And then right here in the middle at 7 is pure water. And ocean water actually sits about right here, about 8.2 on a pH scale, all right? So it's slightly basic. So when you guys hear ocean acidification, that does not mean that the oceans are turning to battery acid, okay? That's not what's going on. In fact, the worst projections are that it wouldn't get much past about here, but that has a significant impact on the organisms in the ocean. And the reason this is happening is back to these little protons. So what pH actually means is it means the power of hydrogen. It means how many of these hydrogen ions are floating around in a solution. So for things that are very acidic, a lot of hydrogen ions. For things that are, excuse me, that are very basic, not so much, all right? And this becomes important because these are very reactive. What happens are those hydrogen ions, because of that little charge, they react with other things. They do their own chemical reactions just by being there. So if you take acid and pour it on something, that things you see in movies where there's this horrible like dissolving of substances, well, that's these ions interacting with those other chemicals. So as we pump more carbon dioxide in the atmosphere, it's going to pump it into the ocean. It's going to pump it into carbonic acid, bicarbonate, and carbonate, and it's going to keep putting out more of those hydrogen ions, and that pH is going to keep moving this way. So that's what acidification means. It doesn't mean it's going to go past neutral. It just means more acidic. And this becomes a problem because the organisms that live there, they have to make shells, they have to make homes, and this disrupts that. The change in the pH in the ocean will disrupt an organism's ability, especially organisms that make shells, all right? So zooplankton, clams, lobsters, right? Well, that's a little bit different. They use a different thing, but anyhow, things like that, this disrupts it a lot, and their shells start to get very thin and brittle, and they can't survive that way. But it also affects, again, nutrient exchange and metabolism and a lot of other stuff. So anyhow, these are some of the things, some of the environmental factors that affect life in the ocean, all right, that affect these food webs and all this complicated interaction, not just that energy transfer up the trophic pyramid, but this balance, if you will. Excuse me. So with that said, we've talked a lot about all the things that affect life, but we haven't really talked about what is life, all right? So this is getting a little bit more philosophical, I suppose. So this brings me to your new questions that I'm going to put on Blackboard, and there are going to be 2 of them. And the first one, I want you to, you can sit back and daydream next to the ocean or in your favorite natural setting, and I want you to contemplate, what is life? What do you think life is? What makes something alive? And then after you think about that, and you think you have a good answer, where do you think it came from? So think about those. Again, do your homeworks, watch the videos, do your reading. Come to me in office hours. If you can't make that, make sure you're keeping in communication with me. Send me emails if you're having problems ahead of time, before assignments are due. And I'll see you guys next time when we're actually going to talk about what is life.